There's something almost hypnotic about watching raw sugarcane transform into those perfect white crystals sitting in your kitchen cabinet. But what most people never realize is that the journey from field to table involves one of nature's most fascinating industrial metamorphoses, a process so intricate that a single miscalculation can ruin an entire day's harvest worth millions of dollars. Right now, across tropical regions spanning 5 continents, massive factories are consuming sugarcane at rates exceeding 12,000 tons per day, yet the average person has never witnessed what happens behind those towering steel walls. This isn't just about making sugar. This is about controlling chemistry, biology, and physics simultaneously while racing against time itself, because once sugarcane is cut, a countdown begins that no amount of technology can stop. Step inside one of these facilities and you'll immediately notice something unexpected. The overwhelming sweetness in the air isn't pleasant. It's almost suffocating, a thick atmospheric presence that coats your lungs and makes you understand why workers rotate shifts every few hours. The thunderous mechanical symphony of crushers, evaporators, and centrifuges creates a soundscape that drowns out normal conversation, forcing communication through hand signals and headset radios. But beneath this industrial chaos lies a precision operation where temperature variations of just 3 degrees Celsius can mean the difference between premium refined sugar and an unusable syrupy mess. Every second, thousands of chemical reactions are occurring within miles of stainless steel piping, each one monitored by sensors that feed data to control rooms resembling something from a space mission. This is where agricultural tradition meets cutting-edge technology, where ancient crops encounter modern engineering, and where the substance that fueled empires and sparked revolutions is born from fire, pressure, and scientific mastery. What makes sugar production so captivating is its fundamental paradox. Sugarcane contains roughly 10 to 15% sucrose when harvested, yet extracting that relatively small percentage requires an industrial process of staggering complexity. Unlike many manufacturing operations that add components together, sugar production is essentially an elaborate separation process, isolating one specific molecule from a complex organic matrix filled with fiber, water, minerals, and countless other compounds. The factory doesn't create sugar, it liberates it from the plant material that has been holding it prisoner. And here's what most people find shocking. Despite all our technological advancement, the basic chemical principles used today were discovered in the 1700s. What has changed isn't the chemistry, it's the speed, scale, and efficiency with which we execute these ancient principles. Consider this remarkable fact. Sugarcane is one of the most efficient solar energy converters on Earth, capable of transforming sunlight into stored chemical energy at rates that surpass nearly every other crop. A single acre of sugarcane can produce approximately 6,000 to 8,000 pounds of sugar annually, which represents an extraordinary feat of natural engineering. But here's the twist. That same efficiency creates a logistical nightmare for processors. Sugarcane begins losing its sugar content the moment it's harvested, with enzymatic reactions converting precious sucrose into less valuable glucose and fructose at an accelerating rate. In tropical heat, a harvested stalk can lose up to 2% of its sugar content within just 24 hours. This biological countdown means that modern sugar factories operate under immense time pressure, often running 24-hour operations during harvest season to process cane while it's still at peak sugar concentration. The global sugar industry produces approximately 180 million metric tons annually, making it one of the world's most significant agricultural commodities. Brazil alone produces nearly 40 million tons each year, operating some of the world's largest sugar mills where individual facilities can crush over 15,000 tons of sugarcane daily during peak season. These aren't quaint rural operations. They're industrial powerhouses consuming electricity at rates comparable to small cities, processing biomass at scales that boggle the mind, and employing sophisticated automation that would impress aerospace engineers. A single large-scale sugar mill represents an investment exceeding $200 million, with equipment that must withstand not just mechanical stress but also the corrosive effects of sugar-laden steam, acidic juices, and extreme temperature fluctuations. Here's something that surprises even food industry professionals. The color of sugar has almost nothing to do with its purity. Raw sugar appears brown not because it contains impurities, but because it retains a thin film of molasses on each crystal surface. The actual sucrose molecule inside is chemically identical whether the sugar appears white, golden, or brown. What differs is the degree of processing, specifically, how much molasses has been removed through washing and centrifugation. This means that raw sugar marketed as more natural or healthful is essentially just less processed white sugar, containing the same sucrose content with a coating of molasses that adds negligible nutritional value while significantly affecting flavor and baking properties. The engineering challenges involved in sugar production are genuinely impressive. Consider the crushing process. Sugarcane stalks are incredibly fibrous, essentially nature's version of reinforced composite material with tough outer rinds protecting juicy inner cores. Extracting juice requires applying pressures exceeding 250 bar, that's roughly 3,600 pounds per square inch, while simultaneously feeding continuous streams of cane through roller mills weighing up to 60 tons each. These massive rollers must be precisely aligned to within millimeters despite handling thousands of tons of material daily. The mills operate in series, typically 3 to 6 stages, with each successive mill squeezing progressively drier bagasse, the fibrous residue left after juice extraction. What happens to all that bagasse? Here's where sugar factories reveal their hidden genius. That compressed fiber becomes the factory's primary fuel source. Modern sugar mills are essentially energy-neutral operations, burning bagasse in high-efficiency boilers to generate both electricity and process steam. A large facility can produce 150 to 200 megawatts of power from bagasse combustion, often generating surplus electricity that's sold back to the regional power grid. This means sugar factories are simultaneously food processors and power plants, converting agricultural waste into valuable energy while eliminating disposal problems. The ash remaining after bagasse combustion doesn't go to waste either. It's rich in potassium and phosphorus, making it an excellent fertilizer that's returned to the fields. The chemistry occurring inside evaporation trains is where sugar production becomes truly sophisticated. Raw cane juice is approximately 85% water and only 15% dissolved solids, primarily sucrose. Removing that water efficiently without destroying the sugar requires multiple effect evaporation. Instead of simply boiling juice in a single vessel, factories use a series of 4 to 7 evaporation chambers operating at progressively lower pressures and temperatures. The vapor from the first evaporator becomes the heating source for the second, which produces vapor that heats the third, and so on. This cascading system extracts maximum energy from each unit of steam, reducing energy consumption by up to 80% compared to single-stage evaporation. Temperature control during evaporation is absolutely critical. Sucrose begins breaking down into glucose and fructose, a process called inversion, at temperatures above 110 degrees Celsius, especially in acidic conditions. This inversion is disastrous because inverted sugars don't crystallize properly, remain in the molasses, and reduce overall sugar yield. To prevent this, operators carefully manage pH levels, adding lime to neutralize acids while simultaneously monitoring temperatures across every evaporator stage. Modern factories employ hundreds of sensors feeding real-time data to computerized control systems that make thousands of microadjustments hourly. The crystallization process represents the factory's moment of truth, where concentrated syrup transforms into actual sugar crystals. This occurs in massive vessels called vacuum pans, which operate at reduced pressure to lower the boiling point and prevent sugar inversion. Operators introduce tiny seed crystals into the supersaturated syrup, providing nucleation points around which sugar molecules can organize themselves into the characteristic crystalline structure. As water evaporates, more sucrose molecules join the growing crystals, gradually building them to the desired size, typically 0.5 to 1.0 millimeters for standard granulated sugar. Here's a fascinating detail about crystal formation. Sugar crystals are naturally perfect geometric structures, specifically monoclinic hemihedral crystals with precise 90-degree angles and flat faces. This isn't an accident of processing. It's the fundamental nature of how sucrose molecules arrange themselves in solid form. The reason your sugar looks like tiny uniform cubes is because that's the most energetically favorable configuration for sucrose molecules to adopt. This crystalline perfection is also why sugar dissolves so readily in water. The regular molecular arrangement allows water molecules to systematically disassemble the crystal structure. Once crystallization is complete, the resulting mixture, called massicrete, consists of sugar crystals suspended in mother liquor, a thick syrup still containing dissolved sugar. Separating these components requires centrifugal force. Sugar centrifuges spin at speeds exceeding 1,800 revolutions per minute, generating forces up to 1,500 times Earth's gravity. At these extreme accelerations, the denser sugar crystals are thrown against a perforated metal basket while the liquid syrup passes through the holes, achieving separation in less than 2 minutes. The crystals remaining in the basket are then washed with water or steam to remove any remaining syrup film. The quality control measures in modern sugar factories would surprise most people. Every batch undergoes rigorous testing for polarization, a measure of sucrose purity determined by how much the sugar solution retains polarized light. Premium refined sugar must achieve polarization values exceeding 99.8%, meaning it's virtually pure sucrose with only trace amounts of other substances. Laboratories analyze moisture content, color, crystal size distribution, and ash content, with any batch failing to meet specifications being reprocessed rather than packaged. The environmental footprint of sugar production has improved dramatically over recent decades. Modern factories recycle up to 95% of their process water, using sophisticated clarification and filtration systems to remove suspended solids and organic matter before reusing water in earlier process stages. Wastewater that cannot be recycled undergoes biological treatment in anaerobic digesters, where microorganisms break down organic compounds while producing biogas that provides additional energy for factory operations. Worker safety in sugar factories demands constant vigilance due to the numerous hazards present. The risk of combustible dust explosions is particularly serious. Fine sugar particles suspended in air can ignite explosively if exposed to sparks or flames. Factories install extensive dust collection systems, explosion venting panels, and spark detection equipment to mitigate this danger. The high-temperature equipment poses burn risks, while the massive rotating machinery can cause catastrophic injuries if safety protocols aren't followed meticulously. The logistics of sugar distribution reveal another layer of complexity. Sugar must be stored in climate-controlled warehouses maintaining relative humidity below 65% to prevent caking, the phenomenon where crystals partially dissolve at their contact points and then recrystallize into solid masses. Packaging must provide moisture barriers while remaining food safe, leading to the development of specialized multi-layer bags combining paper, plastic, and sometimes aluminum foil. The economic impact of sugar production extends far beyond the factory walls. In many tropical developing nations, sugar represents a critical export commodity and major employment source, with entire regional economies dependent on successful harvests and efficient processing. Brazil's sugar industry employs over 1.5 million people directly and supports millions more in related sectors like transportation, equipment manufacturing, and agricultural services. Technological innovation continues transforming sugar production in surprising ways. Artificial intelligence systems now analyze real-time data from thousands of sensors to optimize extraction efficiency, predict equipment failures before they occur, and adjust processing parameters faster than human operators could manage. Drone technology monitors sugarcane fields, using multispectral imaging to identify irrigation needs, pest infestations, and optimal harvest timing with precision impossible through traditional field inspections. The historical significance of sugar cannot be overstated. This simple molecule literally shaped world history. The demand for sugar drove colonial expansion, fueled the transatlantic slave trade, and sparked numerous wars and political conflicts. Caribbean islands changed hands between European powers dozens of times, with control of sugar-producing territories considered vital to national prosperity. In the 17th and 18th centuries, sugar was genuinely more valuable per pound than many precious metals, affordable only to the wealthy elite. Now let's examine exactly how raw materials arrive at the factory and the complete manufacturing sequence that transforms them into finished sugar. The process begins in the fields. where sugarcane reaches maturity approximately 12 to 18 months after planting, depending on variety and climate. Harvesting occurs through two primary methods: manual cutting, still common in regions with steep terrain or small-scale operations, and mechanical harvesting using specialized machines that can cut, strip, and chop 100 tons of cane per hour. Transportation from field to factory operates under intense time pressure due to the sugar degradation mentioned earlier. Trucks, tractors with trailers, or even dedicated railway systems move harvested cane to the factory, where it's immediately weighed on truck scales to determine payment to growers and track daily processing volumes. Upon arrival, cane is either processed immediately or temporarily stored in cane yards, where it's arranged in carefully managed piles and sometimes sprayed with water to slow deterioration. The cane cleaning process removes dirt, rocks, and trash that could damage equipment or contaminate juice. Cane travels on conveyor systems through dry cleaning stations where powerful fans blow away loose leaves and debris. Magnetic separators positioned along conveyors capture any metal objects, pieces of harvesting equipment, wire, or tools that could catastrophically damage the crushers. Clean cane then moves to preparation equipment including knives and shredders that slice and tear the stalks, breaking open the tough outer rind and exposing the juice-containing inner tissue. The crushing sequence extracts juice through progressive pressure application. Prepared cane enters the first mill, where massive grooved rollers compress it while extracting approximately 70% of the available juice. The partially crushed material then moves to the second mill, where a process called imbibition begins. Hot water is sprayed onto the cane mat, dissolving additional sugar from the fiber before the next crushing stage. Each subsequent mill applies imbibition water, squeezes the cane, and produces progressively more dilute juice. The final bagasse emerges from the last mill containing less than 2% moisture and minimal residual sugar. Juice clarification removes suspended particles, proteins, waxes, and other non-sugar components that would interfere with crystallization. The process begins with heating raw juice to approximately 105 degrees Celsius while adding lime, calcium hydroxide, which raises pH from acidic to slightly alkaline. This pH adjustment neutralizes acids that would invert sucrose during heating, causes proteins and other colloids to coagulate into larger particles, and forms calcium salts with certain organic acids. The heated, limed juice then enters massive clarifier tanks where gravity settling occurs. The settled mud isn't discarded. It still contains significant sugar trapped in the precipitated solids. This mud undergoes filtration using rotary vacuum filters, large rotating drums covered with filter cloth that dip into the mud slurry. Vacuum applied inside the drum pulls juice through the cloth while solids accumulate on the surface. The recovered juice returns to the clarification process, while the filter cake goes to the fields as organic fertilizer rich in phosphorus, calcium, and organic matter. Clarified juice enters the evaporation train, that series of vessels operating at progressively lower pressures. In the first effect, juice boils at approximately 115 degrees Celsius under slight pressure, producing vapor that flows to the second effect where reduced pressure allows boiling at 105 degrees Celsius. This continues through typically 5 effects, with the final effect operating under vacuum at temperatures around 65 to 70 degrees Celsius. The juice progressively concentrates, transforming from the consistency of water to something resembling honey. The concentrated syrup emerging from the evaporation train contains approximately 65% dissolved solids and must be further concentrated before crystallization can occur. This happens in vacuum pans, which are essentially giant pressure cookers operating in reverse. The vacuum lowers the boiling point, allowing further water removal at temperatures low enough to prevent sugar degradation. Syrup is fed into the vacuum pan and concentrated to supersaturation, the point where the solution contains more dissolved sugar than it can normally hold in stable solution. Crystal growth must be carefully controlled through a technique called feeding. Rather than adding all the syrup at once, operators gradually introduce additional syrup while maintaining vacuum and temperature, allowing crystals to grow steadily without creating new nucleation sites. The art lies in maintaining the delicate supersaturation level, high enough to sustain crystal growth but not so high that spontaneous nucleation occurs. The process continues until crystals reach the target size, typically requiring 3 to 4 hours for a complete batch. The finished massacrete is discharged from the vacuum pan into crystallizers, large U-shaped troughs with slowly rotating agitators. Here, the mixture cools gradually while gentle stirring prevents crystals from settling and agglomerating. Cooling causes additional sugar to crystallize from the mother liquor, maximizing yield. After several hours, the massacrete moves to centrifugal stations for separation. The white sugar discharged from centrifugals contains approximately 0.5% moisture and must be dried to reach the standard 0.03 to 0.05% moisture content required for proper storage. Drying occurs in rotary dryers, long, slightly inclined rotating cylinders through which hot air flows countercurrent to the sugar. The tumbling action ensures even drying while the hot air carries away moisture. The dried sugar then passes through coolers where ambient air reduces its temperature to prevent condensation when packaged. Packaging operations vary depending on whether sugar is destined for retail or industrial customers. Retail packaging uses automated bagging machines that weigh precise quantities and seal bags at rates exceeding 1,200 bags per hour. These machines incorporate metal detectors to ensure no contamination, check weighers to verify accurate filling, and date coders to print production information. Industrial customers receive sugar in bulk, 1-ton super sacks, 25-kilogram bags, or direct truck loading for very large consumers. The molasses separated from sugar crystals still contains 30 to 40% sugar along with other dissolved substances that prevent further economical crystallization. This molasses has significant value. It's sold for cattle feed, providing energy and minerals, fermented into ethanol for fuel or beverage alcohol production, or used as a feedstock for producing baker's yeast, citric acid, or monosodium glutamate through industrial fermentation. Quality assurance laboratories analyze samples throughout the process, testing incoming cane for sucrose content and fiber levels, monitoring juice purity after clarification, checking syrup concentration before crystallization, and verifying final sugar meets all specifications. Modern laboratories use sophisticated instrumentation including near-infrared spectroscopy for rapid composition analysis and automated polarimeters to measure optical rotation with extreme precision. The factory's control room resembles a high-tech command center, with multiple monitors displaying real-time data from every process stage. Operators monitor flow rates, temperatures, pressures, levels, and equipment status, responding to alarms and making adjustments to maintain optimal conditions. Modern distributed control systems allow remote operation of valves, pumps, and other equipment, with automated sequencers handling routine operations. Maintenance operations run continuously, as equipment operates under harsh conditions that cause inevitable wear. Crusher rollers require periodic resurfacing to maintain the grooves that grip cane effectively. Evaporator tubes accumulate scale deposits from minerals in the juice, requiring regular cleaning. Centrifuge baskets wear from the abrasive action of spinning sugar crystals, needing replacement after processing millions of tons. Factories typically schedule major maintenance during the off-season between harvests. The integration of all these processes into a smoothly functioning whole represents a remarkable achievement of industrial engineering. From the moment cane enters the factory until finished sugar emerges, typically just 8 to 12 hours elapse, a remarkably short time considering the complexity of the transformations involved. This rapid processing is essential given sugarcane's perishability, requiring factories to operate as finely tuned continuous flow systems where material constantly moves forward through each stage without significant delays. So the next time you sprinkle sugar in your coffee or bake cookies, you'll know the extraordinary journey those crystals completed. From photosynthesis in tropical fields, through crushing, clarification, evaporation, crystallization, and centrifugation, emerging as the pure white crystals that sweeten our lives. If you found the sugar production process fascinating, you're going to love discovering how another tropical fruit makes its journey from tree to table. The modern papaya factory uses completely different technology to transform delicate fruit into products ranging from fresh-cut pieces to concentrated enzymes used in everything from meat tenderizers to medical applications. The precision required to handle papaya without damaging its delicate flesh, the surprising uses for every part of the fruit including seeds and skin, and the high-tech sorting systems that can detect ripeness invisible to the human eye. It's an operation that will change how you think about this common tropical fruit. That video just appeared on your screen, and trust me, the papaya processing innovations you're about to see will blow your mind. If you enjoyed this behind-the-scenes look at sugar production, hit that subscribe button so you don't miss future factory tours. And here's a question for you. What surprised you most about how sugar is made? Was it the time pressure to process cane before it degrades, the fact that factories generate their own power from bagasse, or maybe the extreme precision required during crystallization? Drop your thoughts in the comments below. I read every single one and love hearing what resonates with different viewers. Thanks for watching, and I'll see you in the next episode.